So in this talk I will formulate a theory of quantum gravity that I proposed 2 years ago, and then since that time I have been working on various applications and ramifications, so I will give a number of results, more recent, about those applications. And I will also at the end make a brief history of precursors of the key idea that's behind this, and the key idea is the idea of fake particles, or phacon. That's how I call it. What is it? So this is a fake particle, or phacon is a new concept, which basically means that it is an alternative quantization prescription. Or I should start maybe by saying that everything here in this approach comes from high energy physics. So you will see it from the beginning to the very end. Even in the classical limit, there will be remnants of this. So this approach is basically the same approach that leads to the standard model, and the theory that I formulate is just one step beyond the standard model. And the extra step, the last mile, is this concept. So basically, you are going to modify the crucial thing in your quantization. This is the first chapter of every book in quantum field theory, maybe, where you have, normally you use the Feynman I epsilon prescription to deal with a propagator, and that's where you have to do something different. And then you have a particle that, at the fundamental level, is not in the set of asymptotic states, and you don't need to wait for it to decay. You don't need to assume that it is unstable. It's really a fundamental theory, the one that you get from this. And in the case of gravity, the fake particle allows you to get rid of ghosts by quantizing them in a different way. They will become fake, and they will be consistent with unitarity, and then you can have this theory of quantum gravity that I will talk about. So I will briefly introduce the theory without giving too many details, because I want to move to physical applications, but I will give you the key points, and the technicalities then are left to the papers. I will then start focusing on the classical limit, and because there are remnants of this fake particles in the classical limit. And I will also apply the new theory to cosmology, Friedman-Robinson-Walker solution, and see what implications there are there to give you an idea of what happens. So basically, a fake particle is an object that in many situations simulates a particle. It's hard to distinguish from a real particle, but it's different because it does not appear in asymptotic states. And so the basic difference is that you can never see a fake particle, and you can see a real particle. But at CERN, we have never seen directly the Z boson and the W boson and the Higgs boson. So the difference in that case has to be tested with precision measurements, because the two things have lead to different physical quantities, even when they are both virtual. So it's an object that you introduce and later project away in your theory, pretty much like the Faddeev-Popov ghosts, which take care of the longitudinal and temporal modes of a gauge field. And to have unitarity, you have a symmetry, the gauge symmetry, that protects you, and you know that you can work with those extra degrees of freedom and later at the very end project them away with no remnant whatsoever.
So may I ask, so big particles, they carry energy?
Yeah.
So
they are purely virtual quanta.
But they can annihilate them and become real particles?
No. They can produce real particles, but they cannot become themselves real particles. So this degree of freedom that you introduce and later project away is in some sense similar to the Fodor-Popov ghosts and the temporal and longitudinal modes of the gauge potential, but it's different in the sense that it is not protected by gauge symmetry. This works for an entirely different reason, and it has consequences. And the first prediction will be that at very small distances, causality no longer holds. There is no ordering of time. So there is no past, present, and future, but still you have a predictive theory at those energy, at higher energies, and even to an amazingly high energy. We conclude at the end with a comment to tell you that this theory will be not only predictive, but perturbatively predictive up to an amazingly high energy. So the problem of quantum gravity is to make it renormalizable and unitary at the same time, because Einstein gravity is non-renormalizable and unitary perturbatively, but you can solve the problem of renormalizability by means of higher derivatives, as you heard in the previous talk. But then you have propagators that make the renormalizability easier because they fall off more rapidly, like 1 over p squared squared. But when you decompose them by means of partial fractioning in simple poles, at least one of them has a minus sign. And if you quantize it the usual way, you will have a minus sign in the optical theorem that you saw before. Instead of having this relation, you will have some minus signs there, and you destroy the optical theorem. This, however, holds if you follow the rules. Now you change the rules. Now the propagator, let me start from an unprescribed propagator with both residues, both signs in front, because everything I'm going to say holds for both cases. Normally you use the Feynman prescription, and the Feynman prescription leads to an imaginary part for the propagator, which is this one, and it is the delta function on shell. That's the particle. Depending on the sign of the residue, you have plus or minus. That's a particle when you have plus, and it's a ghost when you have minus. A ghost is like a -1 particle, and that's why it is unphysical. Now let's see what a fake particle is. Well, you should have a 0 in front of the delta function instead of plus or -1, and this is something that you can easily get by making this trick, introducing a width epsilon like that, which is 0 on shell. However, this is very delicate, because if you take this thing seriously, that's nothing but the principal value, the Cauchy principal value of 1 over p squared minus m squared. There is a reason why it has not been considered. Actually, in the end, I will tell you that it has been considered, but this is completely inconsistent inside Feynman diagrams. And indeed, well, you can take it, but then you have to know, to complete the prescription, to tell I have to tell you how to use it inside Feynman diagrams, and it's not a principal value, because you have to start from Euclidean space and rotate, Wick rotate. The Wick rotation is not analytic, and so on and so forth. So there is a procedure in Feynman diagrams that is a little bit complicated. You have to specify which integration paths you have to integrate along. You have to even complexify the space components of momenta, loop momenta, and deform the domains of integration. After you do that, something that I learned by studying the Liebig models, some higher derivative models proposed in the late 70s, the answer, thanks to a nice mathematical theorem, is very, very simple. And that, luckily, allows you to make all sorts of computations. The answer is as follows. Take, for example, the bubble diagram. This is the simplest diagram you can consider. This is a self-energy. If you compute the self-energy with a Feynman prescription, or yes, with a Feynman prescription, and you plot the amplitude as a function of the external energy, complexified P0 external energy, you should also study it as a function of the full complexified external form momentum, but let's just keep it simple here, and we have just the plane for the energy. Then, okay, this is the imaginary axis where you have the Euclidean, and there is no problem there. And then you find two branch cuts on the real axis. What are those branch cuts? Thanks to the optical theorem, they correspond to a threshold. That's the branch point. And above the threshold, you can turn, associating this to a cut diagram, you can turn the two virtual particles in between into real particles. So that's where the physical process takes place. And normally in the bubble diagram, inside the bubble diagram, these are virtual particles, but the discontinuity or the imaginary part of this amplitude, discontinuity, the difference between what you get from above and what you get from below, gives you, by the optical theorem, a cross-section. A cross-section for what? For the production of those two particles in between. Now, if those two particles have to stay virtual forever, as I want, that cross-section should be zero, and that imaginary part should be zero. Now, the Feynman prescription is the analytic continuation. It's Vic rotation analytically. So this is the imaginary axis. You rotate, and that means that you reach this portion of the real axis from above. In the and here from below. In the conjugate amplitude, Feynman with Feynman prescription, you reach it from below, and the discontinuity is, by the optical theorem, a cross-section for this process. Now, after the study of pinchings, deformations of contours, and all that in the case of a fake particle, the result is amazingly simple. Namely, you just take the arithmetic average of the two analytic continuations that you get from above and from below. That's a non-analytic operation, but it is completely unambiguous. It cancels the imaginary part. It returns a second analytic function above the threshold, which will no longer be analytically related to the analytic function you get below the threshold. So you get an analytic function here, which is exactly the same as you have with Feynman. And with this non-analytic procedure, we'll get a second analytic function inside the cut, if you want. It's not from above, it's not from below, it's inside. If you want, you can enlarge the cut into a cone to make it more visible that you will have two disjoint regions of analyticity. And then the theory is unitary. And this you can generalize to all orders and all diagrams, as you can check in the papers. In formulas, if you are familiar with this kind of computations, the bubble diagram leads to this formula by means of Feynman parameters. It's the integral of certain logarithm with this prescription. And with the Feynman prescription, you get 1/2 the logarithm of the argument squared. And that breaks the domain into two disjoint analyticity regions. The real part will be the same. You see two analytic functions. And the imaginary part will be 0 for the Feynman, and for the Feynman, it's a square root above a certain threshold, and that's the cross-section for the production of the two particles, which from virtual turn into real. And so in the case of the Feynman, they never turn into real. So this peak, you would still see the peak at CERN in case of fake particles, but you would never find the particle as a real particle. So in the case of quantum gravity, it's quite natural now to take back those higher derivative theories that have the so-called ghost and quantize the ghost as a Feynman. And that's it. That's the theory. The theory will change, of course, physically, completely, but it's conceptually very simple. So you take a higher derivative action, which is made of the cosmological term, the Hilbert term, y squared, which can be expressed like that, and r squared, with parameters alpha, psi, and zeta, which are a little bit redundant here, but I use a redundant parameter because the normalization is different at low energies and at high energies, so which one is chosen to be one doesn't really make much sense. But these three parameters have to be positive to have at least positive square masses in the poles. So what you can cure is the negative residue of the ghost, but I cannot cure tachyons with this. So you better assume that all masses squared are positive. So if you quantize it as usual, this theory is Taylor theory, has a ghost, and the solution is to quantize the would-be ghost as a fake. And you can couple it to the standard model, of course, covariantize in the way you like. So to make things more explicit, let's add auxiliary fields in order to eliminate the higher derivatives and write everything in terms of plane two derivative actions. And then you need two more fields. One is a scalar field phi, and one is a spin 2 tensor chi mu, symmetric tensor. And then your action turns into a non-higher derivative action, which is made of the Hilbert term for gravity. Cosmological constant is 0 here for simplicity. A very nice action for the scalar phi, which is the Starobinsky action, with the positive coefficient, with a nice potential. This is very good. And then a very complicated action for the spin 2 tensor, which is implicit here. But when you make it more explicit, you will find that apart from interactions and non-minimal terms, it's a Pauli-Fierce action with the wrong sign in front. That is what would be the ghost. So to make sense of this theory, have unitarity. Chi mu should be quantized as a Facon. And in this way, you have both normalizability and unitarity at all energies. I'm not advocating that these, at the fundamental level, I'm not saying that these Facons, these would-be ghosts, have to decay, they are unstable. This is a clean, clear, and radically new quantization of the theory. Phi is fine, but that doesn't mean you cannot virtualize it as well, because the procedure is totally general. You can even apply it to a physical field, and so you can ask yourself why phi should be, even if the residue is positive, why should it be non-fake? I cannot have an answer, so phi could be either a fake particle or a physical particle, and if you want, you have two possibilities, and only experiment could discriminate between the two. So in the end, you have a theory that's described by a triplet. One is the fluctuation of the metric around flat space. Let's call it a graviton. Then you have a massive phi and a massive chi mu, and the masses are determined by the parameters we saw in the action at the beginning. These are the only two new parameters with respect to Einstein gravity. And you can do more computations. This transparency is just to convince you that in this theory you can do computations as you do with a standard model. So for example, you can compute the bubble diagram for the graviton self-energy and or the Facon self-energy, and you can resum the bubble diagrams to all orders as you usually do to compute the width. And the width of this Facon, which is related, by the way, to the central charge C in a funny way, where NS and F and NV are the number of vectors, fermions, and matter fields, matter scalars.
So on the previous slide, if you add the chi mu to the G,
This auxiliary field is introduced as a shift of the metric to diagonalize the various pieces. Otherwise, it's.
So well, now is there an ambiguity which is kind of the right or the true?
An ambiguity of what kind?
Well, once you added the chi as a shift, and in addition to the standard H mu.
No. This is you add an auxiliary field just to avoid these squares, r mu squared. You write r mu to make it simple as r mu squared as r mu chi mu plus chi mu squared, right? So I'm doing nothing, but I'm eliminating the higher derivatives this way, and then you make the shift to diagonalize. That's all. That's all I'm doing.
Since, I mean, of course, G has a typically has a definite signature. I mean, just adding stuff to G is not necessarily innocent.
G will have the same signature, yes. Chi mu will have to be treated as a field. So this is, if you want, it's a shift of H, because G mu will be eta mu, the flat space matrix. This is perturbity, right? So
yeah.
You don't have.
But you said also earlier, I will just push this to arbitrary. I mean, perturbation, it will be basically, I guess, chi and h can also become big.
We'll see at the end.
You'll see.
Can become big. Well, no, the answer is it will never become big up to very, very high energies. So like the standard model, it will have a range of applicability where it is perturbative, and then hopefully you would have to get some ideas on how to go beyond the perturbative expansion when it is not perturbative, as in QCD. But I will show you at the end that this theory is perturbative up to an amazingly high energy. So this negative gamma means that causality is violated. A negative width is inverts past and future. Because if you put a negative width, take a bright Wigner and study the Fourier transform without assuming that gamma is positive, then you will see that the theta function selected the past or the future is the theta function of gamma t. So if gamma is positive, as usual, you select the past, otherwise you select the future. That means that if you study the response of a source with that green function, when gamma is negative, this theta in front will project the integral from t to infinity. So basically you need to know the source, the cause in the future to predict the future. That's how you violate causality. That's not a big deal actually, because there is this factor. The green function is made of a damping factor, but even without the gamma, which is a quantum effect, this is a very rapidly oscillating factor, which averages the entire effect to zero. So basically it's like saying that to predict what happens in the next hour, you need to anticipate what will happen in 1 divided by m time. And that, if m is even smaller, much smaller than the Planck mass, the mass of this phaton could be, for example, 10 to the 12 GeV, much smaller than the Planck mass, this time would be 10 to the minus 36 seconds, 20 orders of magnitude away from the precision we have today. So this is perfectly consistent with data, but we will come back on these numbers and these bounds, experimental bounds, later. So what I'm telling you is that the key solution is having a degree of freedom that is not in the asymptotic states at the fundamental level. Not because it disappears because of funny dynamical phenomena. It's really in the fundamental theory. So, and what does it mean? I want to move to the classical limit because the funny thing is that this effect survives the classical limit. The violation of microcausality and many other things, even in the classical limit, could be studied, and that would allow us to maybe go beyond the perturbative expansion. Basically, a field that is not a state, a particle that is not in the asymptotic states, in the functional integral doesn't have a source. There is no source for the phaton. Or if you go to the gamma functional, that source equals 0 means that you are solving the equation of the field and inserting the solution back into the action. How do you solve this functional equation? Here I'm talking about Feynman diagrams. This is a set of Feynman diagrams, that the ones I told you before, that you have to compute with the phaton prescription. And so there is, when you solve this equation, there is no freedom, no initial condition, no final or boundary conditions that you can choose. It's everything blocked by that prescription. And this is what you do in the classical limit. So basically, to find the classical limit, you have to do the same. The classical action I told you before, the higher derivative one, is not the classical action. No matter how you write it, if you write it in the higher derivative form or in the non-higher derivative form, because it has something bad still, the phaton. So the true classical action is obtained only after you project it away, precisely as you don't take as a classical action a gauge fixed action with Popov ghosts. You first eliminate, and then you have f mu squared. That's very nice classical action. Here you have to project the phacons away, but then the result is not as nice, and it switches on many new properties and phenomena. So basically, let's write it in the non-higher derivative form where you have three field equations, and if chi mu nu is a facon, you should solve this one with its own prescription and insert the solution in the others. And if phi is also fake, you should do the same for that. And this brings very unforeseen features in the game. Well, first of all, the facon prescription, now you are in the classical limit, tree level, no funny integration paths, no integration domains, no loop integrals. So there you can just take the propagator, I wrote it as it appeared, the principal value. So the classical limit of the facon propagator is the principal value. Don't use that in Feynman diagrams because it is dangerous. You cannot understand what the quantum origin of that classical limit is just from its classical limit. And so the other point is that since everything comes from high energy physics, it is formulated perturbatively. So I know this projection only perturbatively. And let's see what funny things it brings into the game, starting from a very simple, clear example that makes it easy to understand what happens. So take a non-relativistic Lagrangian, normal m v squared over 2 plus an external force, and add higher derivative term. Okay, that's the game is what happens there if I want to treat the higher derivative terms with a facon prescription. Well, the equation of motion looks like this. You have the external force, and instead of being F equal ma, you have an additional higher derivative term. But the kinetic part factorizes two operators. One is the usual second derivative, and the other one is the one whose pole would be the fake particle. So you take this, you invert it, and throw it to the right-hand side by means of the principal value, the facon prescription, and that's what you get. Instead of having F equals ma, you have ma equals to a certain average of F, and the average is calculated with a strongly oscillating function. Assume that this time tau is 10 to the minus 36 seconds. And this is the violation of microcausality. And if tau goes to 0, of course, you get back F equals ma because this tends to the delta function. Okay, so that is what you get. That's the type of classical theories that you get. And why you still have the violation of microcausality at the classical level, in the classical limit. Microcausality only because you just need to anticipate a little bit of future to predict the future and not a true violation of causality. The point is that this is simple because I have an external force, but as soon as you try and add, for example, a self-interaction, like pi to the fourth, and you apply the machinery, then you get into something interesting. Basically, when you want to, again, the projection is known only perturbatively, and this is hard to do, to study perturbatively. What you get is that if you apply the machinery, you will end up with an equation of motion, the projected one, which contains infinitely many terms, and the Lagrangian infinitely many terms. But not only, the terms you get are an asymptotic series. So basically, this is a remnant of quantum field theory, because in quantum field theory, you deal with asymptotic series all the time. But now you have it in the classical limit. So unless I can use, I have a reason to use, to trust the perturbative expansion, whenever I need an exact result, I am in trouble, because I have an asymptotic series. And you can check, for example, that the coefficients of the Lagrangian or the projected equations of motion grow like, they blew up very rapidly, they grow like n factorial to the fourth. And you can check that the behavior of the solution numerically is the typical behavior of asymptotic series, namely the first truncations get very precisely the behavior of the exact solution, and after a few approximations, when you exaggerate and you demand too much, you don't have any connection with between the approximation and the exact solution. Let's see what happens when you apply these theory ideas, implications on the Friedman-Robinson-Walker metric, for example. This is the metric where d sigma squared is this object. I'm not assuming zero curvature. Everything is general. In the case of this simple metric, the spin-to-field decouples, basically, because it's coupled only to the Weil tensor, and the Weil tensor for this metric is 0. So you just have g mu nu and phi. And basically the higher derivative action is just the Starobinsky action, r plus r squared. So unless I am assuming that phi is a Facon in itself, this is nothing new with respect to what you would normally do. So let me assume that phi is also a Facon, and let's see what happens in that case. First of all, you have to write down the unprojected equations of motion. Here they are. I don't think that people notice that written in this way, they factorize two operators in a very nice way. That's crucial for the projection I want to make. But it's true. Without these two objects, you would get the same as in the Einstein theory. And the only modification are two differential operators in front. One is the sigma, with one derivative and two derivatives and the Hubble constant there. And one is upsilon, which is sigma plus function. So fine. Mimicking what we said before, if you want to project phi away, you should invert this operator and throw it to the right-hand side with a universal Facon prescription. And the same for upsilon. Well, this is easy to say, but not so easy to do. But anyway, if you would do that, the invert operator would give you an average, which is the sum, average sum, the principal value, if you want, or the average sum of the retarded and advanced potentials. And the advanced contribution is the violation of microcausality. So you get two equations that look like the ordinary Friedman equations with some average to the right-hand side. The point is that the average depends on A itself, so it must be solved self-consistently, and this is quite hard. Or if you want, you can introduce certain combinations of the pressure and energy density so as to make them look like exactly the Friedman equations with the modified pressure and density. So again, if you try and solve these projected equations, the very same projection being around in these averages generates asymptotic expansions, but you know, like in quantum field theory, but you know that even in quantum field theory, we manage from time to time to have exact results. For example, anomalies can be easily resummed to all orders because they are one loop exact. All corrections are 0. Or the renormalization group flow, which is an anomaly, the anomaly of scale invariance, and it's a resummation. Or the widths we saw at the beginning, in the middle, which are a resummation of the bubble diagram and a geometric series. So here too, there should be some situations where miraculously you can go through all the problem and maybe find exact solutions. And here is the example. There are two examples. One is the case of radiation. P equals rho divided by 3. That's the state equation of radiation. Another case is vacuum energy, cosmological constant. And the third case is a combination of the two. And those can be solved exactly because basically one of these two, this or this one, are 0. And the average of 0 is 0 non-perturbatively. Perturbatively as well as non-perturbatively. That's the only information you use. And then this is the solution. If you are curious, just the curiosity, it's interesting because it's almost like the solution you get in Einstein gravity. There is only one small correction, which is the solution A of t and rho of t depends on three constants, sigma, sigma double prime, and sigma prime, and the relation has a small correction this one with respect to the Einstein solution. That's all. Okay, so in general, if you take, for example, dust, the other situation that's interesting for cosmology, radiation, vacuum energy, and dust. In the case of dust, nothing simplifies like this, and you would get asymptotic series. But there are some situations where the violation of causality, where the universe conspires to make itself causal. For example, if you study the equation of a scalar field with a source in a background, the Friedman-Robinson-Walker background, then you again get this operator sigma, and assume that the Hubble constant is constant in some interval of time, and then you can use the Fakon prescription to study the green function with a non-zero h. Well, it turns out that a non-zero h eliminates completely the violation of causality, because you get a theta function that is ht. So if h is positive, then the contribution of the advanced potential disappears, and you only have the contribution of the retarded potential. So maybe positive h is what gave time a direction at the beginning of the universe. Still, there is one thing, because these equations have to be, even at the classical level, interpreted in a new way, and the solution, even if you don't have any contribution from the future light cone, but only from the past light cone, so causality is fulfilled, because this is the solution. The integral is from t to minus infinity. It's to minus infinity. Everything comes again from particle physics, and in particle physics you have scattering processes, and scattering processes compares minus infinity to plus infinity, and there is no minus infinity in the universe, and certainly we cannot reach plus infinity in time. But this is what particle physics is. So basically you have a problem that's defined only in an interval of time, but the solution requires you to give knowledge about the source in such a far past that it's outside your problem. Well, the consequence of that is an uncertainty or fuzziness, which is classical, survives the classical limit, although it has a quantum origin, because the most you can do is to write this solution where you integrate from t1 to t. So the extra piece is a constant, but it's something you don't know anything about. However, since this function is rapidly oscillating or even damped, you don't really make a big mistake for long intervals of time. So basically, you have to reduce the window of your classical problem. The classical problem equation is defined in this interval, and you will have full predictivity in a slightly smaller interval, where this delta tau is 1 over m, the Compton wavelength of the Fakon. Because everything else will be, in this error you make, will be basically suppressed away. So we have 10 minutes. I see. Some people ask me, can this violation of microcausality be amplified? No, it's short range, because if you write the propagator in coordinate space, it's a Yukawa potential mirrored to the future, because you have the advanced potential, but the Yukawa potential is short range. And let me remind you that the shortest amount of time that has been directly measured is just 10 to the minus 17 seconds from laser pulses. And the shortest distance that has been measured directly is from LIGO, 10 to the minus 70 centimeters. This is seconds, this is centimeters. So there is a speed of light in between, which means that time is measured with 10 orders of magnitude in accuracy more than space. And this is still 20 orders of magnitude away from the times I'm talking about. So which means that the predictions of this theory, even including the violation of microcausality at small distances, are fully consistent with data. Now let me conclude with a brief history of the quest for purely virtual quanta. There are some precursors, traces of similar ideas in the past. Of course, this was not present, the Fakon. But you can start from an idea of Dirac. You can find it nicely explained in Jackson's book on classical electrodynamics. When you have an accelerated charged particle, it radiates, and you can express the radiation as an effective equation of motion, which is higher derivative, and factorizes again an operator. And the idea of Dirac was to trade the runaway solution for violations of microcausality. Basically, you take this operator, you invert it with a prescription, however. Since tau is the electric charge, you should have the result regular when tau goes to 0. So this is not a Facon prescription, but it is a nice classical argument. And when you do that, the answer is unambiguous, but the integral you get is from t to plus infinity. And so you violate microcausality because there is always a damping factor, so you just violate causality by a small interval of time, which is, in this case, this number, which is, for the electron, 10 to the minus 23 seconds. Still much smaller than what we can measure. Then there are the Leavick models. There are particular higher derivative theories proposed in the end of the 60s by Lee and Vick, which soon realized that they were not formulated completely, but the Facon ideas allows you to understand them but much better. Basically, they have a particular kind of Facon around when their formulation is completed. But they soon realized that if you would ever solve this problem, you would run into the violation of microcausality. And then there is another idea by Feynman-Wheeler electrodynamics, which studied this propagator, the principal value. And of course, that would be a massless, the analog of a classical analog of a massless Facon, and then the Compton wavelength would be infinity, so you violate causality, not just microcausality. And so they had to come up with a very involved emitter-absorber theory that you can look up in the literature. These are their papers to recover causality. Some people, Bollini and Rocca in particular, took this propagator seriously inside Feynman diagrams. You might remember Bollini and Giambiagi, those who invented dimensional regularization. They are Argentinian physicists. And they claimed they could make sense out of it inside Feynman diagrams. That's not true. And I will write a paper to make everything clear on this soon, because I see that people don't have it clear. If you use this inside Feynman diagrams, you violate renormalizability because you generate very bad non-local divergences like this. And you violate unitarity and you violate stability. But this proves that there was some interest in something purely virtual. And I think that the Facon is the right and definite answer. About causality, you should also be aware that there is no notion of causality in quantum field theory, aside from quantum gravity, in the standard model. This is Tofton-Weltman diagramma, where they warn you that Bogoliubov's definition is of shell, it's not something observable, and the Lehmann-Simansek-Zimmermann definition of commuting fields outside for space-like separated distances is also a non-observable definition. It depends on the gauge fixing, it depends on... So in my personal view, it's very hard to elevate microcausality to a fundamental physical principle. It was already hard in the standard model, but quantum gravity, the one I formulated, gives the final blow to it. At certain distances, it doesn't occur. But that doesn't mean you cannot study scattering processes at even smaller and smaller and smaller distances. So probably it is a blunder due to our limited insight, and we may downgrade it to an unusual form of the equations where there are these oscillating averages, which still allow us to make predictions and test the predictions. So to conclude, I think that this is the approach of quantum gravity that is as close to the standard model as it can be. There is no other approach that is just in that spirit. So first, it's a quantum field theory. It's perturbative. It can be. It's an approach which is as perturbative as the standard model. You can make calculations with the same techniques, and you can, of course, couple it to the standard model. It's rigid. You cannot play games and adjust everything you want, like in supersymmetry, string theory. When something is not good, you add parameters. There are only two parameters here. The theory is unique. It's the unique theory which is strictly renormalizable, like the standard model. It's fundamental. This solution is fundamental as the standard model. I'm not claiming that you can make sense of the ghosts because they decay. That would not be satisfactory from a high energy physics point of view. It's like saying that you neglect the muon because it decays. Well, the muon is there, and you can see it before it decays. So if you have something bad like a ghost, even if it does decay, it's still there, and in principle you can see it, and you will see minus 1 probabilities, negative probabilities. And the last comment is that this theory can be predictive up to a fantastic energy, because just think that the fine structure constant of this theory is, as I showed in the calculations of the gamma, the width before, is the ratio between the Facon mass and the Planck mass. So suppose that the Facon mass is 10 to the 12 GeV, much lower than the Planck mass. Then this ratio is 10 to the minus 14. And to reach a non-perturbative region, the only thing that can happen is a running, but the running is a logarithm. And to beat this, you need to go to this fantastically high energy. That means that if we were able to make progress at a speed such that we can increase by a factor of 10 the energy we reach, the maximum energy per year, in 20 years we get to the Planck scale, and to reach this energy it will take 1,000 times the life of the universe. So to the people of asymptotic safety, I think I can say that this is pretty safe enough itself. Thank you very much.
Yes, thank you so much. Questions?
So you have to choose a specific value for the higher derivative couplings to avoid the tachyons, if I understood correctly.
A specific sign.
Specific sign, sorry. So I'm wondering whether the result, I mean, your theory would be asymptotically free, because to get asymptotic freedom in high derivative, there is a specific choice of sign.
No, it's the other sign. This theory is not asymptotically free.
So is it? Is it UV complete?
What do you mean by UV completion?
I mean, if it's not asymptotically free, do you have to impose a cutoff or to avoid Landau?
It's like the standard model. Standard model is not.
Standard model is not UV complete.
If you want to say so, yes. It's there is a beta. The beta function of one coupling tends to 0, and the beta function of the other coupling instead behaves like the beta function of QED or couplings like that. It could tend to a fixed point, but it doesn't really matter here because the goal is to get something that is as close as possible to the standard model. So.
Yeah, about this micro-causality. Of course, in multi-jet physics, you have basically the radiation reaction with a much stronger coupling constant. So in principle, I suppose you would be able to see it there.
To see the violation?
Yeah, because it's alpha S, it's a strong coupling, but the jet fragmentation and multi-dual emission, these are the things people look at.
I know there are some proposals to do that, but I have to say I'm very skeptical. You will be definitely able to interpret that as a violation of microcausality. We can discuss it privately. It's a very hard concept if you think to prove that something is a cause of something else. Just think of it.
Well, if I go to the doctor and then I die.
No, I can disprove that in a minute. I can disprove that in a minute, because in a deterministic setting, the past determines the future in the same way as the future determines the past. So if you are deterministic, there is no cause and there is no effect.
The energies you reach here, so they are far above Planckian.
Yep.
So and these are the real energy, I mean, like gravitational energies. In the sense, of course, that we have, just arguments that why do things become very non-perturbative when you reach Planck scales? Well, because energies become so large that you reach, black holes form all over the place. So how is that here?
Yeah, here the expansion parameter is this one. And since the theory is renormalizable, because if it were not renormalizable, you would add terms one by one, and those would be weighted by the inverse powers of the Planck mass. And so infinitely many would become suddenly important at the Planck scale. But here the theory is renormalizable. So the 2-3 terms I have, they are those. And the expansion parameter is this ratio. And what can beat that? Not the energy. It's like in QET or QCT. It's not energy divided by mass, because this is a dimensional coupling now. The theory has a completely different power counting. So it's not energy divided by Planck mass, which becomes 1 at the Planck scale. It's this, and this becomes 1 only by logarithmic effect.
So what happens, does anything happen to black holes? I mean, if I just naively extrapolate, it's just a classical solution. To very high masses, or mass densities.
That's one of the projects I have now, but what do you expect to happen to black holes?
Well, should I still expect them to be there? And then I do potentially run into an issue, that things start collapsing into black holes just because energy density.
I think I cannot give you an answer right now. That's something that I have to look at.
Because it's classical. It's one of the typical arguments why people argue